So, here we are. I've got some homework problems up for today. If you had a chance to look at those, I also have those on here so we can work through some if you would like to. Yeah.
Can we go through number 8 on the 2014 practice exam?
Sure. All right, so we're looking at the 2014 practice exam, number 8. And so let's take a look at what we've got. So the first thing in every case, the first atom connection in every case is going to be a carbon. So that doesn't help us out much. So what we're going to do is then look, we can then look for the second thing attached, or the one with the thing 2 bonds away, and see what's the heaviest. And so initially, we see that this group right here has a CO bond. And so we have an oxygen 2 bonds away. So that automatically gives it number 1, because in this case, we're bonded to 1 carbon and 2 hydrogens. In this case, it's 2 carbons and 1 hydrogen. And here, it's 1 carbon and 2 hydrogens. So number 1 definitely goes to this, this methanol-looking substituent. Okay, so then let's see. We can compare this one, which is connected to 1 carbon, 2 hydrogens, and we can see that this is 2 carbons. So definitely this is higher priority than that. And so similarly, this is just connected to 1 carbon, so this is going to be number 2, ultimately because the first point of difference is going to be a carbon versus a hydrogen in that case. And then finally, we're comparing this one on the far right and this one on the far left. So they're both connected, so this carbon is connected to 1 carbon, and so is this one, so we have to count even further. And so this carbon's connected to 2 carbons and 1 hydrogen. This one's connected to 3 oxygens. And so since oxygen is heavier than carbon, we know that on the one on the far right should be higher priority. So we end up saying 1, 2, 3, 4. Question about this one specifically. Just try to stay on topic as we talk. Who does it? Oh, yeah, sorry.
So you're just looking at the very first carbon after the dash?
Well, it depends on if we see we have the same group. So the first thing we want to pay attention to is the first atom. But in this case, they're all carbons, so then we have to start comparing the next thing attached. And so we start looking for the first point of difference, and then when we find the point of difference, we go with the heavier atom. All right, next question. Sarah.
Can we go over number 2 from the 18?
Number 2 from the 18. All right, so the one, let's see, which one?
It's that one.
This one right here?
The bottom, like number 2.
Oh, this one down here. Okay, so this is going to be a little bit similar to what we did today, right? So we looked at some examples where we had an acyclic structure, and so in this case, I asked you to figure out what the starting material is. So you can see that in this top case, we've added 2 bromines to a molecule. That's literally the only thing we've learned that a reaction could provide in terms of these substituents, right? We have added hydrogens to things, but we've certainly never added methyls. And we've also never added 2 hydrogens at the same time to another one. So the only thing we can do is brominate. All right, so furthermore, we know that a bromination reaction goes through a halonium type 2 mechanism, which is going to go through 3 green, so we get an anti-stereochemistry. So what we've got to do is we've got to orient this molecule such that the bromines are anti to each other. And so fortunately, as I've actually drawn it, they are anti to each other. So if we look over here, we can see that the bromines are on basically opposite sides. So just like we did in class today, we're going to look and see which substituents on the front carbon and the back carbon are going to be on one side of our bromines. And then we look for the substituents that are going to be on the other side. So we see we've got a methyl and a hydrogen on the same side. So we can put that here and here. And then we've got a hydrogen and a methyl. So we put that there and there. And so we see that that gives us the E double bond in that case. Only the E double bond, or the E alkene, is going to provide that exact stereochemistry in the product. Yeah, we can do the bottom one too. Yeah?
I don't quite understand. Can you explain more how you go from the Newman projection to like adding the constituents on like just the...
Yeah, and so what it is, we can draw this maybe a little more clearly. First of all, let's color code. So what we've got is basically we compare, let's see, we compare these groups together because clearly they are on the same side of each other when if we use the bromine as basically the line down the middle, right? or the two bromines. And so in doing so, essentially, that bromine line, let's see, we'll use blue, kind of looks like that, right? And so we imagine that's where our new double bond, or the double bond that was there would be, okay? So what it is when we come over here and draw, we want those blue things to be on the same side. So if we're going to kind of be looking in this direction, C1 has a methyl and C2 has a hydrogen. So this would be the blue substituents here, and then likewise we would have the gray substituents on the same side, like that. And so basically what it is what we want to keep in mind is when we add this, when we go about our anti-addition, in fact what we could do is we could go ahead and draw out how we get to that product. All right, so let's do it like this. So let's take that E double bond. I'm going to try to add some space in here. I think I can do that. Pretty fancy, huh? Okay, so let's take that same exact E double bond and see what happens when we brominate. So we can turn it on edge a little bit. I think that makes it a little more easily seen. So by turning it 90 degrees, we're going to start out with C1 and C2. So we'll put methyl back there, our hydrogen back there, hydrogen in front, and methyl in the front. Okay. Make sure I know what I'm doing here. Okay, so we're going to brominate. And so what's the first step of this mechanistically? We start an arrow where? At the pi bond. And so we're going to attack from the front side, from the top face, of our alkene. And so when we do so, what kind of intermediate will we form? A halonium, right? And so specifically we'll be forming a bromonium. And so that bromonium, since it has to be a syn addition, so the bromine has to attach from the same side to each of those carbons, we end up with a structure that will look kind of like that. And so as this bromine approaches from the top face, it pushes our substituents down, right? And so our hydrogen and carbon 1 will still be on a dash, but it'll be sort of angled down, and so the methyl will have the same situation. And so likewise on the other side, our methyl will be pushed down a little bit, and so will our hydrogen. So we need to remember our plus charge there. All right, so we've got a structure that looks kind of like that. And so now what we can have occur is we have that other bromine floating around. Let's make a little more space. So we've got our bromine floating around. And so how does that bromine, this remaining bromide ion, have to attack? From which face, top or bottom? Is it going to be syn or anti? It's got to be anti, right? And so what's anti to the top? It's going to be the bottom. It's got to attack from the bottom. If we're going to displace one of those carbon-bromine bonds, then we're going to have to attack from the opposite side of the carbon to push that bond away. All right, so which one do you want to attack? The one on the left or the one on the right?
Right.
Doesn't really matter, yeah. So we'll attack the one on the right. In this case, there's no difference. And so what we'll do is we will, in fact, attack that on the right side from the bottom. Now, however, what do you think is going to happen to these substituents when we attack from the bottom? They're going to get pushed up, right? Because our bromine has to be on the bottom. It has to attack from that bottom face. So what we'll end up with is we're going to snap that three-membered ring open. And so we will end up with this stereochemistry on the left. So likewise, we will end up with a bromine down in the plane, and then our wedges and our dashes pushed up. So we have hydrogen. We have methyl right there. Okay, so I guess the point of this is if we look back at our double bond, we can see that we've got a red hydrogen and a red methyl on the same side, right? And so likewise, we can have a blue methyl here and a blue hydrogen. So these things, these color-coded are on the same side of each other. And so when we look down at our product that results, do we have the same case? Do we have our red hydrogen and our red methyl on the same side of the resulting product when we show these bromines anti? Yeah, we definitely do, right? We have the hydrogen on a dash here and the methyl on a dash there. And so likewise, we have our methyl in front and our hydrogen in front there. And so what that tells us is that the orientation of our substituents here, they're going to be the same as our orientation and our substituents up here, assuming that the two things we've added are bromines in this case. We are showing anti because we know it has to go through an anti-addition. Now, if we were doing a syn addition, what we would have to do is the two things we've added, for example, we could have added diols using osmium tetroxide. We'd have to rotate this such that the diols were syn to each other. And then again, it's going to be the relative orientation between the red group and the blue group versus the red group and the blue group here too. And so red and red are on the same side here, and they're going to be in the same side in the double bond. Yeah.
Is it wrong just to look at like what you give us minus the bromine and see that it's E, and then know that like if it's in the right position, like
Yeah.
if it's in the anti, then
Yeah, and the more of these you do, the less rotating and drawing you'll have to do. What you said is exactly right. So when we look at this original structure, if you're getting pretty good at being able to look at these and sort of see what's going on in space, really we've already got the bromines anti to each other, right? So one we've got up and on a dash, and one we've got down and on a wedge. So they are already anti to each other, but again, you have to be able to really kind of think about what this looks like three-dimensionally and maybe not draw it out at least a little bit.
what if it was on a dash? What if both of them were on a dash?
If both of them were on a dash, well then they're not anti to each other. And so when we try to consider what our starting material would be, we have to think first, well, what kind of mechanism is it, so we know if they need to be syn or anti. And then once we've got them aligned that way, then we can pay attention to where the other substituents are in space.
What if it was up and on the wedge?
The bromine up here.
What if the bottom? Oh, okay, sorry. What if the bottom bromine was up and on a dash?
If it was up on
the
a
wedge.
dash, well then we've got their syn.
Okay.
Right, but that doesn't, that product that we would get from the relative orientation would not be correct because we know that the bromination must be anti. Yeah, and so you do always have to keep in mind what mechanistically, how are these things going to go. All right, let's, Rhea, about this?
Yeah.
Okay.
So with the one that you just showed with the red and the blue,
Yeah.
oxidant, would it
Yeah.
matter if you switched like the MEs to the other side, if they were still anti from each other?
As long as you, as long as you've still got the EO bond, it's the same molecule.
Okay.
So you can draw this any way that we learned to draw.
Okay.
So I just show it like this, I guess. I don't know why I should like that. I don't know.
Okay, thanks.
Yeah. All right, so let's go ahead and look at that second one. And really, this one is going to be even, I should have made these more challenging. All right, so what kind of reaction have we learned that can produce that product? It's, well, not a halohydrin, just a halogenation, right? Because in a halohydrin, we add a chlorine, or we would be adding a halogen plus water. All right, so in this case, we're doing a halogenation, so specifically it's a chlorination, right? We learned that we can treat a double bond with the Cl2, and so ultimately that will lead us to that chlorination. Now, this one's a little easier because if I already drawn this product out with the chlorines in an anti-position, yeah, and so we know because this is a chlorination, it has to go through a type 2 mechanism, which gives us anti-stereochemistry. And so pretty much we do the same thing. We can see that we've got a hydrogen on a dash and a methyl on a dash, and then we've got a methyl on a wedge and a hydrogen on a wedge. And so the starting material that would lead us to that would be the double bond, where we've got a methyl and a hydrogen on the same side. And so then we'll have the basically, and so this is more or less the what we can call the wedge side. And down here we have what we call the dash side.
And is it okay if you reverse them?
As long as you've got the same stereochemistry, as long as you've got 2-butene that is, that it has correctly drawn in the E orientation, yeah, doesn't matter. Questions about these? Okay. Oh. down. We'll call this number 1. And so this is what? 4-methyl-3-heptene. And we are chlorinating it. Okay, so let's go down here. All right, so 4-methyl-3-heptene. Is that 4-methyl? Is that correct?
Yes.
Okay, so we're chlorinating. All right, so let's see. Again, the same mechanism. We know we're going to have what kind of stereochemistry? It's going to be syn, right? And so we won't, let's see. Did I ask you to draw mechanisms for this? Okay,
Why is it gonna be what?
did I say syn? I meant anti. I'm so sorry. Okay. I'm glad that you panicked, though. That's good. All right. Good. Yeah. Jeez. Scary. Okay. So basically, I'm going to go ahead and draw the product first. And so the reason I'm going to draw the product is because we're going to use that information about it being anti to quickly see what we've got. So if we draw the anti-product, let's go ahead and draw 1 chlorine on a wedge here. What will the chlorine be at that secondary carbon? Will it be on a wedge or a dash? It'll be on a dash, right? So that's the quick, easy way. As long as you've got a nice, neat zigzag like this, when we say anti, that means they will just, in fact, be on opposite faces of our zigzag. And so we've also got the possibility of forming the other enantiomer. So in that case, our methyl is pushed forward. We've got a chlorine on a dash. And so that means the other chlorine will be wedged. All right, so that's a nice thing about the zigzag drawings. As long as we keep them on a nice neat zigzag like they are, we'll end up, anti things will be on opposite faces and syn things will be on the same face. Yeah?
You have to draw the hydrogen that is dashed.
You don't have to. Nope, it's always implied. So in that first structure, we'd have a hydrogen here on a wedge, and then over here we've got a hydrogen on a dash. But ultimately, drawing all those hydrogens in is really just kind of muddle up your picture, right? You can make it less clear, really.
Separating entires.
Yeah. Yeah. Just about this? More questions about this?
Is this all?
Yeah, and so I guess I did ask you to write a mechanism for it, right? So let's do that. So I'm going to say that let's see, we've got I'm going to redraw this. I'm going to say that's a propyl group. That's a methyl group. And so we've got then an ethyl on the same side of the double bond as our methyl. So we would have ethyl here. And then what's on a dash? Yeah, it's just a hydrogen. Okay, so knowing that we're going to go about the chlorine, and honestly, I think it can be a lot easier if we simplify our structures when you're drawing mechanism, right? So we know, what's a propyl group?
3.
It's 3 carbons, right? It's a 3-carbon long chain, and so we've got a propyl group there. So we've got chlorines. And so we can attack from either the top face or the bottom face. Which do you want to do? We'll go top face. All right, so approach top face. And so what we'll end up with is a structure where if we're going to go top face, we'll end up with a 3-membered ring that looks like this. And so what's happening to all those substituents as our chlorine comes in from the top? They're getting pushed down. All right, so they'll look like that. That. All right, so we still got some Cl- in there. And so, when our new Cl- comes in, we've got to think 2 things. We've got to think regioselectivity and we've got stereoselectivity. So, first off, regioselectivity. Is it going to attack the carbon on the left or the carbon on the right?
No.
Which of those carbons would be a more stable carbocation? Left. And so that's the easiest way to remember that. It's going to add to the carbon that is the more stable carbocation. Do we remember why that is? Do you want to go through why that is? Yeah, so the reason is, let's walk through this really quickly. If we have an intermediate that basically looks like this, so we've got chlorine plus, we're going to have this thing actually in equilibrium with a couple of other different species. And so what those species are is we can open our ring up like this. And so we draw equilibrium arrows because it is truly in equilibrium. So it's in equilibrium, or our chloronium is in equilibrium with a carbocation that looks like this. It's also in equilibrium with a carbocation that opens up the other direction. And so if we open that way, we're going to be in equilibrium with this structure. And so which is the more stable carbocation? Right here, the red one? Yeah, it's definitely the red one. And why is that?
Because it's a tertiary.
Yeah, exactly. We've got a tertiary carbocation versus a secondary carbocation. And so what that means is that even though these things that I've circled, the red structure and the blue structure, they're not going to make a huge contribution because they're open shell, the fact is they do make a little bit of a contribution. And so because this tertiary carbocation structure makes more of a contribution, that means that we're going to end up with a little bit more of a positive charge on that carbon on the left. And so up here, we would say that we've got a little bit more partial positive there, a little bit of partial negative there. Yeah?
So if we were, let's say it was HCl, and we were asked to attach a hydrogen in the first step,
Yeah.
would we attach it to the more stable one or the less stable one?
So we would attach, if you're going to add acid to a double bond, you're going to attach it to whatever position will produce the more stable carbocation. And so in this case, we see that the more stable carbocation would result from the positive charge on the left. And so if we were protonating a double bond, or an alkene that is equivalent to this, we would protonate this carbon because that way we would produce the more stable carbocation.
Okay.
If we added the hydrogen here, we would end up with the less stable carbocation on the right. Okay? Yeah.
So
I'm confused about why you're even forming a carbocation, because if you are adding that chlorine to it, then it'll kick off the other chlorine and both carbons will be making 4 bonds.
Say that again?
Like, when you add the chlorine ion to it,
You're talking right at the bottom of the structure? Or like
like in the next step.
in the next step, okay.
Like, the chlorine adds to both carbons, right?
So,
In the first step, like from that.
yeah, it's
it adds-
basically, it adds cement.
And then you're gonna add the Cl minus to one of the other carbons.
Right.
And that's gonna bump the chlorine that's already attached to away. So
Yes.
you're not even forming the carbocation because they're all gonna have 4 bonds.
And so what it is this is an intermediate. So since it's an intermediate and it sits in a valley, it means that it exists for some length of time. And so whatever length of time that intermediate is existing, it has time to basically undergo a little bit of equilibrium into these other species. And so as it's undergoing this equilibrium, we find that it basically forms the red one slightly
So
more.
it's almost like before attaching to the second chlorine, it's like preparing itself to do that.
Yeah, because remember, even though we might, this intermediate might not live very long, electrons are zipping around really, really quickly. And so just if it's a split second, the electrons still have lots of time to pretty much be everywhere they want to be. So we have every possibility down here basically occurring. Is there another question? Okay, so again, which carbon are we adding to, left or right? Left one, okay. All right, so we're going to add to the left one, and we add to the left one because of that partial positive charge. So in doing so, what we're going to end up with is, all right, so our chlorine on the left side will be on the bottom. What's happened to these groups right here? Where do they get pushed in space? They get pushed up in space, right? They get pushed up by our incoming chlorine, and so they keep their wedges and dashes as is. So likewise, our chlorine has popped open in this direction. So we have hydrogen and ethyl there, like that. Okay, so of course, we don't just have this product, what else do we form? Yeah, we also have plus enantiomer. And so how would the first step be different to form the enantiomer here? Yeah, we just start out from the bottom face instead. And so we would end up with the enantiomer of this structure, where these four groups are actually pushed up, and the chlorine has formed a three-member ring on the bottom.
Is there like an arrow starting from one of your electrons on the fluoride to the carbon?
You mean this arrow right here?
Those reagents.
Up here? And so yeah, the two arrows we draw, we start an arrow at the pi bond going to one of the chlorines, and then the other arrow is the sigma bond between these two chlorines breaking and going to form a new lone pair.
Is there like a method for the third arrow?
Not in a halonium mechanism. We've seen that third arrow in some concerted mechanisms, but in the halonium mechanism, that first step is just two arrows. And that's because we're forming one bond and we're breaking one bond into two arrows. Other questions about this?
So you transform the molecules to just be the double bond and constituents, and then how would you determine which one would go on and which one won't?
So what it is if we're going to attack this double bond for the top side, the wedges and the dashes stay the exact same. It's just they get pushed down, right? So when they get pushed down, this propyl, which was on a dash, it's still just on a dash, where we're not actually changing where the propyl and the methyl are.
Right, but from the original, how did you, in the original picture, it's just like.
Sure.
they
And
are
so,
necessary.
yep, and so if we wanted to work backwards, if I said, all right, which alkene could possibly provide this product, you'd want to do a couple of things. First off, you see that it's a chlorination reaction, right? And so you know that because we've added two chlorines. So then, we know that a chlorine reaction has what kind of stereochemistry? Yeah, it has anti-stereochemistry. So have we aligned our chlorines in an anti-fashion? We haven't. So what we look at is we see, all right, the methyl and the E. The methyl and the ethyl are on the same side, right? They're both on wedges. And so that means up here on the alkene, the methyl and the ethyl will both be on the same side. And then vice versa, we've got the propyl and the hydrogen on dashes, and so we want to make sure that those are on the same side as well. If we saw that, let's say, the ethyl and the H were swapped, and we had the different stereoisomer here, but then we would end up with the other stereoisomer on the double bond. So really what it is it's how these things are oriented in the product once we have our things we've added aligned in the correct way, and then we just basically transfer this stereochemical information back up into the double bond.
So you would have to have like a picture of the product to be able to go and actually show them what is that for the first part. Okay.
Can we go over the, like, first one on, yeah, the first one on number 3 of the 21st?
The first one?
Yeah.
Yep. So it says predict.
The first one on number 3.
Oh, like number 3.
Yeah. So
This one right here.
yeah.
Yep. And so, all right, a few things. What kind of reaction is it? Yep, it's an oxymercuration reduction. And we know that just because, well, I mean, I guess anytime you see mercury in this chapter, you know it's an oxymercuration. Well, that's not reaction. So, what is the ultimate product of an oxymercuration reduction? Yeah, it's an OH, and so is it a Markovnikov or anti-Markovnikov addition of the OH? It's Markovnikov, right? And so because, and I guess furthermore, the stereochemistry is what, syn or anti? It's anti, right? And so the reason is it goes through a halonium type mechanism, even though it's not a halogen. So the two things, even without needing to draw a mechanism, we know that it's going to be the Markovnikov regiochemistry So furthermore, we are going to get the anti-stereochemistry. All right, so what that means is that in terms of products, if we have our, let's see, so if we end up with our OH on a wedge, it's not going to matter how we align the hydrogen, right? Because there's two hydrogens here on this secondary position, so we're not going to have a stereo center. And then also we could have the product where the OH is added from behind. So in that case, we would have OH and a wedge there. So what's the relationship between these two molecules? They're diastereomers, right? So what we want to do is when we're doing these, and I'll write explicitly on the exam, I'll say that you don't have to draw all the products. You can draw plus enantiomer, or you can write plus diastereomer, right? So you can draw one product and say plus the other stereoisomer specifically, but just make sure that you are cognizant of whether or not you're going to make an enantiomer or a diastereomer, because if you say one but it's the other, then I can't give you credit for that other structure, right? Yeah, it's about this? No. There's a question about this right now. Yeah.
For the first one that you drew, if you had the OH on the dash, would it be the same one as the second one you drew?
Ask that again.
Sorry, it's kind of confusing. Does the OH need to be the lower one, or can it be from behind? Does that make sense?
So are you asking about the wedges and dashes, how they're oriented on the paper?
I'm asking, I'm asking about the OH. Does it have to be closer down? I don't know. I can show you a picture.
Can it be above the letter?
Yeah, absolutely. The way that our wedges and dashes are oriented don't matter.
Okay, that does sense. Okay.
Because it's the same information. So if instead of having a dashed methyl here, we had a wedged hydroxyl, or a wedged OH, and then here we have the dashed methyl, we're saying the same exact thing. Yeah. Not that we'd have the same picture. And so here we have a relationship where these are diastereomers. Why are they not enantiomers? Yeah, we already had a chiral center set here, and so you can see that it's not changing between the two. Only the new chiral center that we formed is different, so we have diastereomers. Do we want to work through that mechanism? Yes? Okay, let's work through the mechanism.
When we're drawing the mechanism, do we have to draw the mechanism of the diastereomer, or can we just draw the mechanism of one and then write the diastereomer?
Yeah, you can just, and I haven't announced this in class, but you can almost be guaranteed that I'll ask you to draw a full arrow pushing mechanism on the exam. That is pretty much standard for an orgo exam, so expect one full arrow pushing mechanism on the exam. In fact, the exam is written, so. Yay. Alright, so we'll call this number 1. So, alright, so what is the first step of this reaction? Where do we start our arrow? Yeah, so we've got mercury acetate. We know that mercury has a lone pair, otherwise it wouldn't go through a halonium type mechanism. And so we start our reaction like this. And so this is an example, I guess, of where we do have 3 arrows, even though it's a halonium type mechanism. Because we have to lose one of these acetates, or agatates, so we draw that back to there. So this initial addition of the mercury to the pi bond, is that a syn or anti-addition? Not the ultimate stereochemistry, but this first step, is this going to add syn or anti? It adds syn, right? It's all happening at the same time here as we form this mercury 3-membered ring, and so we're going to end up with a structure. Let's attack from the front face. So we'll have mercury, acetate both on wedges. And then we say that we've also got water in here, and so what we do is we attack either the top tertiary carbon or the bottom secondary carbon. Which do we attack? The top. Why? It would be the more stable carbocations for the same reason that we attacked the bromonium ion, more stable carbocation earlier. So our second step. Now, if our mercury's in front, how does our water have to approach? It has to approach from the back. Anytime we're going to do a displacement reaction, we have to undergo our backside attack. And so if it's going to approach from the back, that means that in this enantiomer, this diastereomer, because this is plus diastereomer, because we could have added our mercury from the back face. All right, so our water for the diastereomer that I've drawn, is that going to end up on a wedge or a dash? And that'll end up on a dash, right? Because it had to approach from the back. Remember though, and I promise this is going to happen to somebody. When you add this water in, you're adding an entire water molecule, right? We're not adding an OH, we're adding an OH2. And so you have to make sure that we go through this intermediate where we are showing that it is still an OH2, right? So we end up with a positive charge on that oxygen. Let's see, we've got our methyl on a wedge and our mercury here. This mercury here should also be positively charged. All right, so we end up with that, but we don't even have a stable intermediate quite yet because this structure is charged. So how do we get rid of that positive charge on the oxygen? Yeah, we deprotonate, and so that's something you've just got to get used to. It seems a little weird to, when you see a positive charge, think, all right, we can get rid of that from deprotonating. A lot of people, I think, are going to want to try to stabilize the positive charge the same way we would a carbocation, right? So in that case, we draw electrons to the positive charge. But anytime we have a positively charged oxygen, you can't stabilize it by drawing electrons to the oxygen. You have to draw electrons to a proton and deprotonate, right? So that the electrons involved in the oxygen-proton bond can snap back to the oxygen and stabilize that positive charge. So we can use water as our base. You could also just use a B. It's perfectly acceptable. And so we don't draw our arrow here, right? Because that would violate the octet rule amongst many other issues with that oxygen. So we always want to draw our arrow to the proton and deprotonate such that we have the electrons from that sigma bond snap back to the oxygen. Yeah, Hope?
Could we use the OAC that we have left over?
You could use the OAC. Yep.
Okay.
Basically, yeah, that'd be fine. Any pair of electrons in there, I'm probably going to be fine with. So, all right. So now we get to this structure. So we finally have our uncharged alcohol. But are we to the end of where we need to be? No, because we've got a big fat mercury hanging off of there. So that's when we do our workup. So that's our sodium borohydride workup. And so essentially, sodium borohydride is an H- donor, right? So it's a source of H-. And so we can take that hydride, we can come in and basically knock the mercury off. And so we end up with this product. I guess that's just it. We just knock it off. We have implied hydrogens there. We haven't formed a stereosemic. So, of course, it's this plus diastereomer because this chiral center never changes.
And that little hydrogen that we use, it's just a given, right? We don't need to it's the hydrogen with the electrons.
It's up to you. Sometimes you'll see people draw them to sometimes, I know it's not there. Or I know it is there because this is neutral, right? So it must be there.
Right, but when we add it, it's just like to be added. We don't have to.
It's perfectly fine. Let's see. Since I've told you these workup steps, we don't worry about the mechanism. You don't have to explicitly show it. Now, in a mechanism, if a hydrogen is involved in a step, you do want to show it before and after so that you can have basically arrows going to it or from it as necessary in that step. So, yeah. Other questions about this? Yeah.
For NAD4, like how come it doesn't just replace
So you're asking why doesn't the NaBH4 add?
Yeah, like how come in the end there's none of that?
Well, so sodium's just a cation. It's just a positively charged ion, so it doesn't want to react with our organic stuff anyway. And so the BH4, so let's see, what does this thing really look like? It's a salt. So we've got Na plus and BH4 minus. But even though it's BH4 minus, the structure of that looks like this, right? And so there's not actually any lone pairs to form a new bond between the BH4 and the carbon, right? Because the boron doesn't have any lone pairs. So all we end up adding, and it's you know, these reducing agents there's a lot of different reducing agents. So this is a really common one. But basically, it literally is just a hydride source. It's a way to add H minus. Yeah. And what it is what you end up getting is basically, if you were going to draw a mechanism, you would start your arrow at that sigma bond, and you would just take the electrons with the hydrogen and go somewhere. Yeah.
Could you explain why the Hg is plus and that's something this positive charge?
Well, because here we're connected to two things, right? And so it's neutral, and then here we're connected to three things. So it's just like water.
Okay.
Yeah.
Would you mind explaining why there's only one mercury on two wedges after the first pair?
So this one right here? You mean right here?
Yes.
And so we treat it just like a polonium. It's the same as if we were treating this thing with Br2, and we just form the three-membered ring. The reason, we've got two possibilities. We can either form a carbocation, or we can form these three-membered rings. And so it's more stable if we can to form the three-membered rings because we're closed shell, right? Otherwise, if we had carbocation, we would have one of these carbons open shell. And so basically, if our electrophile here has a lone pair that it can redonate back into that carbocation to stabilize it, it'll do so. And we know that it happens because if we run this reaction, we see anti-stereochemistry. And if we're going through a carbocation, would we see anti-stereochemistry? No, we wouldn't see any stereoselectivity at all. So, yeah. Questions about this? Abby. Yeah.
So, you do number 13 on the practice test?
2015, number 13. Everyone knows that I've posted answer keys to the exams, right? Those are just where in the same folders where the practice exams are. But again, I recommend that you not ruin that resource for yourself by seeing the answers without taking the exam first. So just treat those wisely. All right, number 13. Is this the mechanism right here?
Yeah.
Okay. So, the mechanism of acid. Let me read it. Yeah, this one's a tricky one. Okay, so it says that it's literally the opposite, right? And we know how we could go from basically that direction, right? And so what we can think about is, all right, what are the intermediates involved? Because basically, instead of we're going from A to B to C to D, we're going to go from D to C to B to A. We're just going to go the opposite direction. And so the useful thing is basically the electron movement is going to be the same thing. So let's do that. All right, so the last intermediate, and honestly, it might be. Let me think how we do it. Yeah, let's start with our double bond. All right, so we'll have this product. And so in black, let's pretend that we are. Hold on, let me see the easiest way to explain this. All right, so let's just think about the intermediates. Okay, so if we're forming our double bond, what intermediate comes basically after the protonation of our double bond here? What do we have? So let's imagine basically we're doing this reaction, which is the opposite, right? So we're going to have H2O with catalytic H2SO4, and so we know that we would end up with a product. Oh gosh, that's even tricky. Okay, remember I did not write this exam problem, so okay. So let's just see if we can go basically backwards and figure out how we would get the starting material. Because we know the mechanism from this to this. So let's do that. All right, so we'll do that. We'll work our way down. It's actually a really good problem. All right, so we've got H2O and catalytic acid. So if we have a strong acid in water, what's the first thing that happens? We form hydronium, right? The strong acid dissociates, and so we end up with H3O+. And so H3O+ is basically going to be our strong acid to kickstart our reaction. So where's our first arrow going to go?
From one of the bonds from the pi bond.
Yeah, so we start a pi bond and we protonate. So this is just reaction number 2 that we learned, right? It's the catalyzed hydration of an alkene. All right, so when we do that, what we end up with is going to be a structure that looks like this. And so this isn't going to be super intuitive because we're working backwards, but okay, so we have this carbocation. Now we look at the product and we see that we've got a quaternary carbon here on the left side, right? All right, so we're pretending that we're working towards this product. Do we have a quaternary carbon over here? Could we undergo some shift and form a quaternary carbon? Yeah, so what if we basically shifted this methyl over to there? Would we form a quaternary carbon? We would. Now, is there a driving force for us to do it in this way? No, but remember, we're working backwards in this case. So let's just see what happens. Let's write it down and I'll explain it. So let's do a 1,2 methyl shift. And so in doing a 1,2 methyl shift, we would end up with this structure. Okay, and so up here we have a secondary carbocation. Down here we have, no wait, this is a tertiary carbocation. Down here we have a secondary carbocation. So in the direction we're drawing this thing, do we have a driving force? We don't, but remember, we're working backwards. And so if we were going the other way, would we have a driving force to go from a secondary to a tertiary? Sure. We know that that would increase the stability. So that's fine, even though we're kind of going the wrong direction here. Okay, and so, of course, we know that we've got then plus H2O in solution. And so can we snap those two things together and basically get us to this starting material? We should be able to, so let's see. We'll have that come in. And so will we have a neutral product at this point? We shouldn't, right? Because remember, and again, it's going to happen to somebody. Someone's going to just immediately have an OH group there instead of an OH2 plus group. But we are adding the water, and the deprotonation is a different step. So then finally, we can get back to our neutral species by deprotonating, and so you can use any base. We'll use water. So we will deprotonate like this. All right, so have we successfully drawn a mechanism using the reaction that we know to basically go from our product to our starting material? Yeah, we haven't. So basically what we want to just do is go the other way. So to do that, let's start with our starting material here. And so the last step we did here, it was the deprotonation of this to form this. So if we were going the other way, what would we be doing? We'd be protonating it, right? Yeah.
So is the other hydrogen implied there?
Yeah. Yep. All right, so we'd be protonating it, right? And so ultimately, what we really have down here is this plus H3O plus. So over here, honestly, this I think is a little trickier than I would have ever thought. Okay, so to protonate, we would start with electrons. We would deprotonate our water. And so what we would do is we would form, and we'll do this later on in class, this type of reaction. We're just not to it yet. All right, so we have that structure right there. And so then how can we go from this structure to this structure? What if we just pop off a water molecule? Will that do it? Yeah, because, I mean, think about it. Here we're basically popping on a water molecule, and so to go from this to this, we just want to pop it off. So that's exactly what happens. In fact, we just have one arrow. And so that arrow will go like that. So we know we're breaking the bond, and the water's going to take the electrons with it, and so we show it going to the oxygen to form a new lone pair. In doing so, we're going to form a secondary carbocation. All right, so then, let's see, we're to this point. So we know we need to go to the tertiary carbocation, and we can just do that through a 1,2 methyl shift. So we can show it there. So we end up with that structure. So then finally, we've got to go from, I guess, this structure to this structure. And so going the other way, we protonated the double bonds. So what are we going to do if we want to go back the other way? Yeah, we'll deprotonate. So we know that we've got a proton on that. And so we want to use, I guess, water. Deprotonate like that, and so that would be your mechanism for that. This is very much a have you absolutely mastered this material for exam 2 type of question. Yeah. Yeah, we've just never done this mechanism, right? So I thought it might be easier. We know this mechanism. We knew how to get from this. Basically, we could start at the product, we could start at the product and get to the starting material. And so I figured if we worked through and saw all the intermediates going from A to F, it'd be a lot easier than to go from F to A. Yeah.
Could you do number 4 on 321?
Real quick, are there more questions on this? Yeah.
Can you just explain again the last part of it, where you're going from the carbocation to the double bond?
This right here, yeah. And so what we're doing is we're deprotonating this hydrogen right here. And so remembering that a deprotonation is just like a baton transfer. That means that if I handed someone the baton, I would keep my electrons, right? And so that's what our molecule does. So the water, I'm losing batteries. All right, so the water is going to, electron pair is going to come in and grab our proton. And so now this lone pair has nowhere to go except back to this carbon. But instead of drawing it back to this carbon, what we can do is just go ahead and form a new pi bond with it. So get right back to our carbon. Other questions about this?
Did you ask us something?
I don't think that I would ask something like this. Yeah.
So the exams are good.
The exam is not printed, it is written. Yeah.
The right side.
The right side, I just wanted to show the mechanism that we know. And then we can see that really to go the other way, it is just jumping from intermediate to intermediate, just going the other direction. Yeah. Rhea.
So would you end up with H3O in this case?
Yeah, you would end up with H3O. And so that's good because then that H3O could go right back to the beginning and start another cycle of our mechanism. Okay, what was it? Which one?
Number 4 on 321.
Okay, so up to this point in class, we had learned that there's these 3 reactions that can form an alcohol. And so in the first case, we see that we've got a lot of possible stereoisomers forming, right? So let's see. We've got, in this case, we've got a syn addition. In this case, we've got an anti addition. But they are all Markovnikov. And so what reaction have we learned will undergo a Markovnikov addition of water to form an alcohol but show no stereoselectivity? Yeah, that's going through a carbocation, right? And so what we've seen in class is that to form water in this way that goes through a carbocation, we react with water, and then what else? acid. And so the reason that we have all these different products is because we have to go through a carbocation, and so that's planar, and we end up with really no stereoselectivity. We get all possible stereoisomers. So in the second case, what we've got, do we still have a Markovnikov addition? Yeah, we still do, but now we're seeing stereochemistry, or at least stereoselectivity, right? And so specifically here, we've added a hydroxyl group to the back and a proton to the front, and then here we have a hydroxyl group on the front and a proton on the back. And so what kind of stereoselectivity are we seeing? It's anti, right? So what I'm talking about is we've got a hydrogen here that we've added, and here we've got a hydrogen that we've added. And so we see that this is the anti-stereochemistry. So what reaction have we learned that gives us a Markovnikov addition of water with anti-stereoselectivity? Yeah, that's our oxymercuration. So to do this reaction, we have mercury acetate and water, followed up by sodium borohydride. All right, and then so final, yeah, question?
How do you know there's not an implied hydrogen on the one above? Like, why is it implied there but not?
You talking about that position?
No, like
On number one.
Oh, there totally is.
Oh.
Yeah, there's always an implied hydrogen if there needs to be a hydrogen there for the charge to make sense. So the only way that we could have a neutral carbon at this position is if there's a hydrogen there. And the only place for it to be is on the dash. Yeah.
This is just like a notation question. If for some reason the implied hydrogen isn't there, will you always show us the positive charge of the carbon?
Oh yeah, I'd have to. Otherwise, we wouldn't. I mean, otherwise I wouldn't be writing clearly about what's going on. All right. So in the bottom case, do we still have the Markovnikov addition? We do not. We now have an anti-Markovnikov addition, and so furthermore, we know that we've added a proton there and a proton there. So is that syn or anti? Yeah, that's the syn addition. And so what reaction have we learned that gives us the anti-Markovnikov addition of water in a syn fashion? So that's our hydroboration oxidation reaction. Yeah, so what we've got is 3 different ways to form an alcohol, and so we can see that depending on which method we use, we'd end up with different types of products. Questions about this? Ree?
Can we do number 1 of the stabilizer?
Yeah. Were there any questions about this? Okay.
The second reaction?
All right, so we're going to work on number 1. And so we see Br2 in water. What kind of reaction is it? What did you say? You said it earlier. It's the halohydrin, right? So we're adding a halogen, and then we're adding a water molecule as well. So when we do this, all right, so a halohydrin reaction, let's see, does it give Markovnikov addition? It does, and everything we've learned is going to give Markovnikov addition unless it's a hydroboration, basically. And so is it going to give syn or anti? It's anti, right? Because we go through a bromonium intermediate. And so that means we're going to have 2 possible products. All right, so we could have... So if it's going to go through a Markovnikov addition, are we going to end up with the alcohol on the top tertiary carbon or the bottom secondary carbon? Yeah, it'll be the top tertiary carbon, so we end up with... basically, we can have it on a wedge, which pushes this back on a dash. And so if the hydroxyl group is on a wedge, what must the bromine be on the secondary carbon?
A dash.
Yeah, we know it's an anti-addition, so we have that product. We would also have the product.
Oh, my bad, sorry.
We would also have the hydroxyl group on a dash, which to be anti, we have to have our bromine on a wedge. So what's the relationship between those two? Those are diastereomers. All right, do we want to work through that mechanism? I see mainly shakes of the head. won't do that. Okay, so, then in the bottom case, what kind of reaction will that be? Yeah, again, it's just another halohydrin reaction, and so again, we're going to get the same stereochemistry and the same regioselectivity. So it's going to be Markovnikov, and it will be anti. So to be Markovnikov, we'll add our hydroxyl group to the tertiary position. So that means that we're going to end up with, let's see, we're going to end up with our bromine on a dash, so that we are anti.
Is it a chlorine, or does that?
Yeah, you're right, it's chlorine. It's okay. It almost always comes back perfectly. Almost always. It's okay. We want to reload page, I think. Yay! So, if we had our hydroxyl group on a dash, we'd have to have bromine on a wedge. Chlorine. Shit. Sorry. Alright. And we'd have our chlorine anti there. So what's the relationship between these two? These are enantiomers. Why are they enantiomers and not diastereomers? Yeah, so all the chiral centers are flipped between these two. Unlike the top case, where just 2 of the 3 are flipped, giving diastereomers. Yeah.
This is probably like a dumb question. So you know how here you have the methyl group next to the alcohol on a wedge and a dash?
Yep.
If when we were drawing our own products, we put the ethyl group on a wedge and a dash and the methyl on the plane of the board, is that okay as long as the Cl and OH are still anti?
Yeah. And so what we could do.
Like I left the methyl.
Yeah, I understand what you're saying. So you're saying that you left the methyl in the plane, and so you would have to have the ethyl on a wedge.
Yeah.
And the hydrogen. Yeah, that's the same state.
And then I left the hydrogen on the chlorine crystal on wedges and dashes reversed. I just switched the wedge and dash to the ethyl.
Yeah, as long as you've got the same stereo center, you're perfect.
Okay.
Yeah. Other questions about this? Yeah.
Can we go through like the whole?
The what?
Can we go through the whole mechanism?
Yep, we can do that. All right, so we're going to take a look at the mechanism. So we'll do the mechanism for the top one. It's a little easier to draw out mechanisms with our cyclic structures. So let's see, we'll call this number 2. All right, so number 2, we've got a structure that looks like this. So what are we reacting with?
BR2 and water.
Okay, so Br2 and H2O. We'll go ahead and draw out our Br2. Okay, so what's the first step?
Taking from the double bond to the bromine,
Yep.
and then from the lone pair.
Perfect. Okay, so the first step is we're going to undergo, well, what type mechanism is this? Carbocation, halonium, or concerted? It's halonium, right? So we're going to go through our 3-membered ring, so that's exactly what we should. We would have, we'll attack from our bromine on the front face. Could we attack from the back face? Sure. Alright, so we're going to have our bromonium intermediate there, and so we've got Br minus, and we've got H2O. And so what's more nucleophilic, bromine minus or H2O? Definitely H2O, right? And so what we will do is we'll start electrons, we want to pop open our 3-membered ring, and so we'll do so by drawing an arrow to the tertiary carbon, because that would be the more stable carbocation. So we've got a partial positive and a partial negative. And so our water, is it going to have to approach from the front face or the back face? Yeah, it has to approach from the back face because we've got to approach anti to our carbon-bromine bond that we are breaking. So we know we're breaking this bond, so our water must approach from the back. Now the group that ends up on our 6-membered ring, is that going to be an OH group or an OH2 plus group? It's got to be OH2 plus, right? Because we're adding water, we're not adding OH. And so we're going to end up with that OH2. It is added from the back face. So our bromine down here is still on the front face. Yeah?
Just to clarify, there were 2 dashes sharing the BR plus and then approach as front.
Yeah. Yep, you got it. All right, so of course, this is plus diastereomer. So all these are going to be plus diastereomer. So how do we get rid of that positively charged oxygen? Yeah, so we want to react it with some base, and so what do you want to use for a base? We just don't want to use the Br minus, because we know that as the conjugate of a very strong acid, it's pretty much a non-base. It has no basicity. But you could just use a B. Yep, that is perfectly acceptable. So you could just use a generic base. And so we want to deprotonate, so we grab one of the protons so that the sigma bond can snap back to be a lone pair and neutralize our oxygen. By the way, for those of you that have had lab, how awesome is it that you're done in like 2 hours?
Less than that.
It's pretty nice, yeah. All right, so we're going to put this plus diastereomer. I know it's nice because we'll be done at like at least by 10:30 or so in the morning. So we got, that's my day. It's pretty nice. Okay. Questions about this? Because what we've got is this chiral center right here is never going to change, right? So since that never changes, but the others do, we don't have here. And that's an important point. You do want to make sure you got good handles on the other. You do have air and work here. Yeah. It is due this week. I'm trying to avoid doing those before they're due, just because some people are here and some are not. But I'm happy to answer a question about the sampling once the weekend gets here or Sunday's workshop. Yeah. Was it about this? No. I did the questions. Okay. All right, I'll come back to you.
Could you do number 2 on
321? Okay. All right, so this one right here? Yeah, so basically this is very similar to what we did in class. And so when we look at this, we have a generic product where we've added an electrophile and a nucleophile. So I say in the instructions that we're going to go through a conservative mechanism, which means that we're going to have to undergo what kind of addition, a syn or an anti? It's definitely a syn addition whenever we're going to have a conservative mechanism. And so what we do is, what we want to do is we want to rotate our structures so that we have basically our electrophile and our nucleophile in a syn sort of orientation. So they're going to end up condensed, basically. And so to do so, it's often can be the easiest way to do that can often be such that we draw a Newman projection. And so I've drawn a Newman projection of that here. And so after we rotate to basically eclipse our nucleophile and our electrophile, I can actually color code this a little better. So hopefully it's a little more clear. So what we can do is basically we look at the substituents and we see which ones are together. So here, we'll color code those blue, and we'll color code these gray. Okay, so what it is on our double bond that's going to produce the stereochemistry, our blue substituents are going to be on the same side, and then our gray substituents are going to be on the same side. So when we look at carbon 1, we say, all right, so in the bottom left, and it doesn't matter, you can start up here, you can start down there, you're going to get the same starting material. We see that we've got a blue hydrogen aligned with a blue methyl on the same side. And then alternatively, we have on carbon 1 a gray methyl with a gray hydrogen. And so we look at that, and we see that it's the E double bond. And so since we have two possibilities, what we're going to find, and this is why I wanted to spend a good chunk of time on this today in class, is that what we find is that the E double bond is the only sort of alkene that is going to give us this stereoisomer. If we had the Z double bond, we wouldn't get that stereoisomer. And so in fact what we see is if we do have that Z stereoisomer down here, now we end up with these two groups. We end up with a diastereomer on it, basically. Yeah.
When I was doing this, instead of like this for the second one, I like rotated the sigma bond between the electrophile and the nucleophile so that they were both on wedges, and then like did it that way. Is that allowed?
Yeah, I mean there's not just one way to do it.
Like, can you rotate that sigma bond?
Well, you can rotate any sigma bond between two sp3 hybridized atoms. Yeah, that's perfect. And that's ultimately what when I rotate this Newman, that's all I'm doing, right? Is I'm just rotating.
Oh, okay.
Yeah. Your question is about this?
Yeah.
Okay.
So I get what we're doing here, like the rotation and like the Z and E, but what does it mean? Like, what are we trying to like find out here?
And so basically, you could imagine a situation where you have to, not form this generic product, but you're asked to synthesize some drug, right, that has specific stereochemistry. And so you know a reaction. So let's just say that our electrophile and nucleophile are, it's like an osmium tetroxide reaction that we know is going to form a diol, and it's a syn addition because the two goes through a concerted mechanism. And so if you want to just form specifically this stereoisomer, what that means is that if you started with this starting material, it's only the E double bond that would allow us to form this because of the syn addition. If we started instead with this Z double bond, or this Z alkene, we would actually form this stereoisomer, and we wouldn't be able to undergo or form this stereoisomer where they're both on wedges. And that impacts a lot of things because keep in mind, we also, these end up being multi-step syntheses a lot of the time. So yeah, we know what product we need here, it requires this, but this might not be available out of the bottom. You might have to make this as well. And so we have to basically connect these pieces together such that we are able to arrive to an ultimate product using basically the tools that we have in our toolbox. And some transformations are a lot easier than others. So let's take a look really quickly. Yeah.
Sorry, real quick. I think you already said this, but for the top, the blue and the gray, it can be switched. Like I could put blue on the bottom and gray on the top.
Sure. Yeah. As long as you've got the E double bond, it's
Okay.
the same thing. You're just looking at it from a different point of view.
Okay.
Yeah.
Sure. Thank you.
All right, so let's also color code this one. So here I have oriented this structure here, and so you can see that now we have these together on one side and these together on another side. And so that means that we're not going to end up with the Z stereochemistry. Now we're going to have a situation where we have a hydrogen on the same side, and then a methyl and a methyl on the same side. So that gives us the Z double bond. And so to add sort of to the question that you had a second ago, it's important because we have reactions that give different stereoselectivity, right? And so we've seen reactions can give us syn stereoselectivity. And so in that case, we want to make sure that our electrophile and our nucleophile are eclipsed. They're syn, right? They're on the same side. But if we were going through a mechanism like a Lonium-type mechanism that gives us anti-stereoselectivity, well, in that case, we need to make sure that our electrophile and our nucleophile are on opposite sides. And so, of course, that would end up changing the stereochemistry. Right, so if these are syn, we'd have a Z double bond, but if they needed to be anti, it would be the E double bond that would give us this product. So ultimately, the stereochemistry of the alkene dictates what the stereochemistry of our product can be. Yeah?
So, how do you determine the NC based on three parts, three
substituents on an alkene? Yeah, absolutely. So what that really would be is for example, if we had a double bond, bromine, chlorine, methyl, and hydrogen.
Oh, no hydrogen.
No. So something like an ethyl.
Oh, I see. Yeah. Okay. Yeah. I see.
You
Okay,
good?
got it.
Okay. All right. Other questions about this? Rachel.
On the 2014 practice exam, can we look at number 11 first 3?
Oh, Fisher projections. Ugh. Okay. So I'm just going to go ahead and say that there's a 100% chance that there will not be Fisher projections on the exam. I think that they are archaic, and so honestly, I'm just gonna let's just forget that one even exists. We don't even want to think about number 3. And then also this. I'm sorry, Rachel. Let's just pretend that they're not even there. Now I hate Fisher projections almost passionately. So yeah, not quite passionately, but almost. Any other? I guess that was.
It's
that.
for that one.
What's that?
It's for 11.
Okay.
How do you know it's meso?
All right, so let's see. How do we know it's meso? So what we've got is this structure. Right here. And so what we're going to do is look for a plane of symmetry if it's going to be, and I don't see any obvious plane of symmetry as it's drawn, but what we could undergo is a 180-degree bond rotation. And so in doing so, we'll hold the left side the same. You don't always have to hold the left side still, but you know, it's easier if you try to stay consistent. And so in that case, what's going to end up on a wedge on the bottom here? Should be the methyl, right? Because it's on a dash going up, and so 180 degrees to a dash going up is going to be a wedge going down. And so we end up with a methyl there and a hydrogen there. And so now I do see a plane of symmetry, right? So now we've got this plane of symmetry right here. And so furthermore, we can make sure that, and really, I mean, because there's this plane of symmetry, we must have a 1-to-1 ratio R to S, but we can confirm that by saying 1, 2, 3, 4. And so is that R or S? Yeah, I see R. And then the other one must be S, but let's confirm. Does that make sense for S? Yeah, it does. So we have our plane of symmetry, we have our 1-to-1 ratio, so we know that that'll be meso. So furthermore, you can confirm that you can always try to confirm that it's meso by checking to see if it has an enantiomer. And so if you mirror planed this, right, if we mirror planed it in this kind of fashion, we would end up with the same exact molecule.
So without doing like the 180-degree shift, could you see it because on each side, like the CH3 is on a wedge on one side and not on the other?
Yeah, so in this case, I guess all of the substituents are 180 to each other, right? So this bromine here is 180 to this bromine here. The methyl is 180 to that methyl, and the hydrogen is 180 to that hydrogen. So if you can see that, you know, that's perfectly fine, but it might be a little easier to confirm just by making sure that you can draw a plane of symmetry. Yeah. Questions about that? Yeah.
Is the reason that number 2 carbons are number 2 priority, is that because that carbon belongs to both the bromine and the methyl group?
Yeah, and so the bromine is definitely going to be first. And so then we've basically got a CH3 versus a carbon over here connected to a bromine. And so since the heaviest thing this carbon's connected to is an H, And the heaviest thing this thing's connected to is a bromine. That one's gonna win. Yeah. Yeah.
How do you know that you have to do these non-rotation? Is that just like during a test, you'd be like, oh, should I just try non-rotation?
It's just one of those tricks. Sometimes you have to orient things a little bit differently to see the symmetry that there is in there. Sarah?
Could you number 11 part 5?
11:5. How many? Oh, that's from chapter like 12. This is basically from like next Wednesday and Friday's class. We didn't get that far.
So we don't.
No. Now you have presumably not heard of NMR up to this point in your life, so don't worry about questions regarding NMR. Yeah.
On the same test, what about number 3?
And again, this is just one of those things that I don't think we're going to cover. We're going to cover hydrogenation on Friday. That's our reaction number 9. But I don't know. I don't particularly love the physical chemistry side of that, so we'll probably leave that out. Yeah.
This is like, well, one question just rose up. There's a question about that on the sapling.
Yeah.
Page 2.
About like the exo, is it like an exothermic type, or is it just asking for the product?
It has, oh, I don't know.
It's probably just asking for the
Okay.
product, in which case we'll get to that Friday.
And then can we go to 318 and do number 1, part 2, like the second reaction in number 1?
This one?
Yeah. Oh, yeah.
So that's
It's
gonna
like
be it.
what confused me about it wasn't really the mechanism, it was that it was all the different products we could get, I guess.
So it's just 2 products, ultimately. It's just these 2 here, right? So because it's going through a carbocation, that water can add in from the front face or the back face of the carbocation, and so we end up with the structure I've drawn plus the enantiomer. You look really concerned. Okay. Rhea.
That package exam we were just on, the 2014 one.
Yeah.
If we look at number 12, I'm not sure if it's like an alcohol test or something we haven't like.
Alright, so in 1,3 butadiene is reacted. Mixture of 2 proteins. Yep, and so this is a pretty good problem. So alright, so we've got a diene now, and we're reacting it with HBr. So that's reaction number 1. This is the first thing we ever learned in terms of electrophilic addition. So what's the first step going to be? Yeah, we protonate the double bond to form a carbocation. And so, in that case, are we going to protonate the primary or the secondary?
The primary.
Yeah, we'll protonate the primary so that we end up with the secondary carbocation. So that's our intermediate. And so, let's see. Alright, so it wants to show the formation of the 1,4 product. Okay, and so what it is we know, yeah, this one's, let's see if she gave any clues here. Yeah, so what it is ultimately is we're going to have, this thing is going to be, have a resonance structure. So that resonance structure looks like this. Right? And so to get to that 1,4 product, then basically we just want to make sure we are adding to that 1 position. Like that. So even though that might not be the more stable product, that And that is this, I mean, this thing is the same as that. We're just showing a different orientation of it, right? Because we've got 1, 2, 3, 4, 1, 2, 3, 4. So it's the same product, it's just turned over. And so, yeah, even though this wouldn't be the major product, it's totally fair. On one of the homework problems I did this, I wouldn't, so, all right, so just start over. If I were going to ask you for a product, I would typically always say, what is the major product? But if I'm asking you to draw a mechanism, I could always ask you to show me a mechanism forming a minor product. And that's what they've done on this exam here. Even though this isn't the major product that forms, it does form, and so they ask you to propose a mechanism that would allow us to basically.
So there's no real shift here, it's just the resonance formed with the
Does it say there's going to be a shift?
No.
Yeah, I don't, let me think, is there any way? I mean, you could, if you had a hydride here shift from the primary to the secondary, you would get to that product, but there's no thermodynamic reason for that to happen, right? And so we wouldn't expect that to be a problem.
Is the only reason the double bond can switch to the other side is because they're directly connected? Okay.
Yeah, they have to be directly adjacent, otherwise, we have to have basically 3 p orbitals in a row interact.
Okay.
So that's what we've got there. We've got the 2 p orbitals of the pi bond, and then we've got the p orbital of the carbon cation. Gabby, do you have a question?
Yeah, I'm not sure if we'll get to this on Friday, but there was a question in Saturday about
Ozonolysis.
Yeah.
So let's see, in section 2, we almost finished ozonolysis today, and in section 3, we're like halfway through. We just started ozonolysis.
Okay.
But we'll definitely
Okay, because there was just one of them, the product was in 2 separate things. It was
yeah, no, we'll wrap that up Friday. Yeah.
Another thing that like Sapling was, this is just like Sapling was telling me things,
Mm-hmm.
and it said if you can't add a borane to a carbon ring, like it was saying like you can't add a boron to a ring. Is that true? Or like, and why can't you add a boron to a ring?
You can't add boron to a ring. Well, how? Acting as a nucleophile or an electrophile?
I remember the problem,
Yeah.
but it was like a complicated cycloalkene with B2H6, and like I tried to add a boron to one of the double bonds on the ring instead of
Yeah.
there was like also double bond on the double bond was the constituent,
Yeah.
and it was saying that you can't add the borane to the ring, you have to add it to the constituent.
Was it a cyclohexene?
It was a cyclohexene.
I'm unfamiliar with that. I don't
Just,
know.
like ignore it.
Yeah, I don't know why you yeah.
Okay.
Unless it's just I can't even think of a good reason why that would be the case. So I don't just ignore it. Yeah. Yep.
Could we do the 2014 number 4?
Put the labeled signal sets in the following. So that's an NMR question. So we're not gonna get to that before this exam. That'll be exam 3. Anytime you see chemical shift or NMR or ppm, that's all NMR stuff. Yep.
You do the second part of number 3 on 318.
The second part of number. Is there more to it than this?
I don't have any more.
Maybe it's 320. Yeah, 321.
Okay. The second part to number 3. What's that?
Never mind.
Okay. Is that it? Okay. Okay, cool. butene have no stereochemistry while 2-butene does. So 1-butene looks like this, and 2-butene can look like this, or it can look like this. And so basically, what we have to do to give stereochemistry or a stereo label to a double bond is we have to be able to prioritize groups. But on this end, whenever we have a terminal double bond, we're going to end up with hydrogens, and so they're the same thing. So we can't prioritize one of those, right? And so since we can't prioritize one, we can't give it an E or a Z label. But if it's 2-butene, now we've basically got a couple of hydrogens off like this. And so we can prioritize. We can say that's 1 and that's 2. That's 1 and that's 2. And so if we can have a situation where the higher priority groups are opposite of each other, we could also have the situation where they're on the same side. And so we give the E label there and the Z label there. Yeah.
Can we ask a question about today's homework or no? Because like not really similar. Okay. Can we do the second one?
Yeah. How did you have time to do today's homework?
Yeah.
I posted that at like 2:45 or something.
We got out of lab and we were like, swim.
All right, which one?
The second one?
Second one?
Yeah.
This one right here?
Yeah.
Okay, so here's an example of an ozonolysis followed by a reductive workup. And so in talking about ozonolysis, it's all about what? Cleavage. It's all about cleavage. Okay. So basically, you can just draw a squiggly line down the double bond, and we're cutting the molecule in half there. So what we're going to end up with is, let's see, we have this structure. Plus this structure. I realize that's kind of small. This is a CH3 here. And so really all it is we cut this thing, and where we had a carbon-carbon double bond, we now have a carbon-oxygen double bond. And it can be a little weird to see sometimes.
So like in the last example we did in class, we had it like bridged, I guess, where like it was. So when you do that versus just immediately cutting.
So the difference there, I know exactly what you're talking about. So the difference there is that we had a ring. And so not only, so we're cleaving this part, but carbons 2 and 6 are still connected together through the other part of the ring, right? And so we end up basically just opening up the ring. We don't end up with two products in that case. So basically you have a ring, and you cut it in, one side of it off, or at least in two, and so you still, if you cut one side of a tire, you still got one thing. Okay, so.
Okay.
Are you going to be asked to draw the mechanism for this reaction?
I would expect you to know this part of the mechanism, but there's a lot of weird funky stuff that happens over there that you don't have to worry about. Yeah. And if you're in section 3, I'm not sure we even got quite to the mechanism today, so we'll start with that on Friday. Somehow section 2 is always just a few minutes ahead.
Also like for this one, just real quick, like it's reduction because it's the Na2S, but it would be oxidation if you had like the H2O2 that we talked about.
Yeah, and so in that case, the only difference would be, so looking in this case, we've got one hydrogen that's connected to one of those carbons in the double bond, and so instead of this being an H, this would now be an OH if we had done an oxidative workup.
Okay.
Yeah, that's the only difference.
And you know that because you add an H2O2 as H2.
Yep, it just depends on whether or not we're going to add H2O2 in the oxidative workup, or if we add dimethyl sulfide in the reductive workup.
is that like the third O disappearing and like when you use like the ME2S?
Yeah, so,
Like we don't have to go through it if we don't need to know it, but just to clarify like how we would apply this, we would just like skip that.
yeah, and so really all I just wanted to show for that mechanism is the fact that it is a concerted mechanism, and so when we add our ozone, you can see we're adding in a syn fashion like any other concerted mechanism. But ultimately, we don't end up with any stereochemistry because we're just cutting the thing in two.
So for something like the one that we just looked at on the homework,
Yeah.
and like you were getting two separate pieces in the end, would the O3 just make like sort of a curve like between them, like connect it? Does that make sense?
Yeah, so let's see what the Wikipedia page says about the ozonolysis mechanism, because I don't remember it off the top of my head.
Like I get how I would draw it on a ring, but I'm not sure when the two pieces are separate. How?
Yeah, and you don't have to worry about it, because you're not expected to know mechanistically when they separate. You just need to know that they do separate.
But like when you're adding in the O3, would you just like put it in between that like like split the double bond and then put like the O3 between them?
It actually, hold on, let me find the intermediate, because it's really, so you add your O3 to your double bond, and so you end up with this type of intermediate where now your carbons that you started with, you've actually got two of the oxygens bridged on the top and then one oxygen bridged underneath. And so it's, do they even show how we do that rearrangement? Yeah, so you end up making the carbonyls, but then they add back in together to form this weird structure, which at that point you do your reductive or oxidative workup. So it's, again, it's just something that's way out of our league right now, I guess.
But if we were answering, would you just not ask us a question like that? When you wanted us to show intermediates with?
The only intermediate I would expect you to show in an ozonolysis is the intermediate I've shown you in class.
Okay. So it would be a ring that we were applying it to.
Yeah. Yep. Yeah, so basically you end up with a 5-membered ring where 3 of the atoms are from the ozone and 2 of the atoms were in the double bond. Yeah. Yeah.
So just to like make sure I understand, when it's cleaved, it's 2 pieces and then it gets double bonds because it's interacting with the oxygen again. Is that why? There are 2 products.
I'm not sure I understand the question.
So like they, in the end, the
Yeah.
the oxygens are bonded. It's a double bond. Is that because the oxygen interacting, or is it always going to be a double bond?
It's, yeah, as far as I know, there might be some modifications to the equation this where you can end up with something else in addition to the reductive or oxidative. There might be other types of workup that you will figure out, but I don't know.
Okay.
So we'll always assume that it's going to end up as a CO double bond. Yeah.
I know you already did this one, but is there any way you like would mind doing one again?
Which one?
It's like it was number 2, the second reaction on 316.
This one right here? number 2.
This is number 2, yeah, that one. This one.
Yep. And so can I just walk you through it? Yep. Okay, so basically the only difference between this one and the one above it and anything we've seen before is as long as we're becoming more and more stable with our carbocation, we can undergo multiple shifts. And so this is reaction number 1. So it's just the treatment of an alkene with a strong acid. And so we protonate the primary carbon. And the reason we protonate the primary carbon is because we can form the secondary carbocation by doing so. Okay, so next door we have a tertiary carbon. And so that tertiary carbon has a hydrogen. And so by undergoing 1,1,2 hydride shift, So basically taking this hydride and moving it to a carbocation, we can end up forming this tertiary carbocation. We have a driving force to do that because we're becoming more stable, right? We're going from a secondary carbocation to a tertiary carbocation. And so then furthermore, this position right here, and this is a special position because it's next to an oxygen, and so of course that oxygen has lone pairs that can potentially donate into a carbocation and close the shell. So in this case, what we see is, in fact, if we undergo another 1,2 hydride shift, so we move a hydride from this position to there, we end up with a carbocation here. And so now we can see that we can draw a resonance structure where we close the shell of that carbocation. So we do 2 shifts. The first shift goes from a secondary to a tertiary carbocation, which is thermodynamically favorable. We're becoming more stable. And then furthermore, from this point, we're going from a tertiary to a resonance stabilized carbocation. And so are we becoming more stable in that one as well? Yeah, definitely. And so in both cases, we're forming a more stable carbocation. And so once we get to our most stable carbocation, it can be then attacked by the bromide. You can show that attacking at either position. That's why I've drawn both arrows. And I should say you can attack either structure. Basically, if you want to draw the bromide going to the carbocation there, as we've learned, that's fine. You could also draw to this structure as long as you just showed this pyrron breaking at the same time.
And where did your methyl go?
Oh, well, it didn't go anywhere. It's just I neglected to draw it. Methyl is still there. Sorry about that. Yeah. Yeah.
Yes. Okay. Can you explain what you meant like at the last part? You can still draw to the pylon as long as you're showing that it's.
Yeah, so since, when we talk about resonance structures, really it's the same thing, right? It's just a hybrid picture of what this molecule looks like. And so what you end up being able to do is you can draw the bromide attacking this carbon in either picture. So we know we can draw it right to the open shell carbocation because it's a carbocation. This is also a carbocation up here, right? Now we're showing the positive charge on the oxygen, but again, it's just a different electronic picture of a carbocation. In fact, it's got a special name. So what you'll find is when you have an oxygen nearby that's able to close the shell of a carbocation, we call it an oxocarbenium cation. And so essentially it's still this carbon here that is ultimately electron efficient. Sorry, I was just trying to avoid your eyes. And so if we add our bromide to this position, this is still the electrophilic position right here. We just need to then show the pi bond retracting back into a lone pair so that we know the overall neutral species.
Okay, so somehow you show that resonance is possible.
Yeah. Other questions about this? Yeah. Did you have a question?
About this, yeah.
Okay.
Is there a reason you can't just shift the hydrogen from like the first step to the third step, like all the way?
Yeah. And so that's just a product or a character of the 1,2 hydride shift. It's got to be directly adjacent. So we've got to do this stepwise one at a time. Yeah. As you go into Orgo 2, you'll find that there are other possibilities in terms of shifting things, but for now we're just going to stick with the 1,2 shifts. Yeah.
So this is back to today's notes that we took from going from the getting the reactants from the products that were formed. I'm just a little confused. So when you rotate the product to make it either whatever it has to be, whether it's in an anti, you can do that because it's a single bond, right? And
Yeah.
it's still the same molecule?
Yep.
Okay, so then you can rotate it to make it whatever it has to be, and then you just do like the new projection to get the original.
Yeah, and so, for example, we showed an osmium, or we showed this diol product, and so we know how we can form diols from an alkene. We can use osmium tetroxide, and so since it's a conservative mechanism, it's going to go through a syn addition. And so since it's going to go through a syn addition, what we've got to make sure that we do is we orient our hydroxyls in a syn fashion, because that's how they will add to the double bond, right? They'll add to the same side. And so when they add, one way you can think of this is when these hydroxyls add to our double bond, what they're going to do is they're going to push these substituents down, right? So we would have a double bond that's perfectly planar, but when the hydroxyl groups add in, this methyl and this hydrogen, they're going to get pushed down. So that's what we're seeing in this product. And so likewise, the things on this side are going to be pushed down. And so what you can imagine is, imagine if we just ripped off the OH groups, and so we went right back to an alkene where these things are going to snap back up to the side. And so ultimately, that is, this alkene right here, right? So basically, I guess what I'm saying is that if we reorient this, if we just pretend that we can remove those OH groups, and our methyls and our hydrogens snap back up into an alkene type position, we would end up with this kind of structure right here. And so that is the E double bond, the same as the answer we gave over here.
Okay, so if you had drawn the wedges and the dashes on the intermediate step, before the final product, if you had drawn the wedges and dashes switched, so you would have the H's up top and on the left, and on the right you have the H on the bottom. It's still the same product, right?
So are you saying, talking about this orientation?
No, the next right one. Yeah, there. So if you have the methyl and the H's like switched positions, I think that's just how you drew it.
That would be the other enantiomer.
Okay.
Yeah, and so in reality, yeah, absolutely, this would provide for the other enantiomer. And that's what we see in the vast majority of these electrophilic additions, is we often end up with product plus enantiomer.
Okay.
And it's because we can add to either face.
Which starting line would you do then? Because they'd still be E, right?
Yeah, and they're still E. Because what it is E can lead to two different products. And so what I can do is I can show you one product and just say, well, how, what double bond would give you this product. It would certainly give you another product. It could give you the enantiomer, but only one alkene is going to be able to give you one specific stereoisomer of the product, yeah. Yeah.
On the same notes.
Sean.
Yeah, Sean.
Okay.
On the same notes for like a little bit down, there was a meso compound I just showed us in class today.
Yeah.
I don't really understand how that's meso, because where did the wedges and dashes have to switch? Does that matter?
Yeah, and so what it is, so what you can do is, how can I draw this? So you're right. If you were to rotate this thing basically on this axis, such that the OH groups come down, and you would expect the methyl to rotate up and be on a wedge, right? But instead of doing that, watch my pen, just do this. Instead of rotating it in this kind of fashion with depth, just rotate it like that. And so if you do that, all right, our methyl is on a dash, and so it's going to stay on a dash when we rotate it like this. And so that's exactly what we see here, see right there, right?
Yeah.
And so that's the rotation you've got to do to see that those are the same thing. Yeah.
It's unrelated, but on the homework from the 16th, the first page, the fourth one down.
The 16th?
Yeah. The fourth one down. I don't really understand why you added the carbocation to the secondary. Why is that something to do with the oxygen?
That's exactly why. Yeah. So since that oxygen has a lone pair on it, it can stabilize the carbocation. And anytime we have basically a closed shell carbocation, that's going to be more stable than any open shell carbocation. So the options would basically, we can have the tertiary carbon here, or carbocation here, which is open shell, or we can have the secondary carbocation that's closed shell. So because it's closed shell, it's more stable.
How do you tell that this is not C?
So you much homework? Oh, on sapling. Check your, go back and check the sapling, because what you're showing me is a structure that looks like this. And so if we show a line drawing of that, what that's indicating is that we've got.
Oh, maybe the sapling, like, it's saying that there is a carbon, and it's like, written, it's like inside that there's carbon or double. But then how would we still know that there is hydrogen in the group that, like the methyl group is connected to which one is on the top?
So basically, we're talking about how do we figure out whether something like this is E or Z.
Yeah.
Yeah, and so what it is if this is a hydrogen, you just prioritize your groups like any other
how do you
time.
know hydrogen is not there?
So, I mean, if we're going to draw this going to the right, we expect this to be an sp2 hybridized carbon that's trigonal planar. So by drawing my hydrogen up, I'm just completing the trigonal plane, right? And so if that's how it's oriented,
that would make sense.
Yeah, then you have 1 and 2, 1 and 2, and so what you've got is an
Okay,
equal.
I think that's,
Yeah, just check it. Yeah, just check it out. 5:55. Let's make it quick. Okay.
Just a quick question. If you scroll back up to the number 1. Looking at the 5th one with the nitrogen, would the lone pair on the nitrogen help out with the carbocation?
Absolutely. Yeah, and so we would end up protonating this carbon because this carbocation is going to be resonance stabilized.
Even though the nitrogen's already stable with that lone pair.
Because the structure overall, if we're going to have to form a carbocation, we can either form this tertiary carbocation, which is just flat out open shell, or we can form the secondary carbocation that could be resonance stabilized with a lone pair. And so if it can be resonance stabilized and made closed shell, it's going to be.
Okay.
Yeah. Sarah?
So this is just really general. When you're drawing a reaction, when you're writing a reaction mechanism, and there is a substituent that's not involved in the reaction, you could leave it stereochemistry totally the same, and not worry about drrawing the enantiomer as a product, because the enantiomer is not going to form when the stereochemistry stays.
It'd be the diastereomer if we're forming new stereocenters, basically.
Okay.
Yeah. Whew. Well, I think it was a productive 2 hours. Let's see how big this video